Hey class, we're back again, and here we're looking at chapter 8.6, and so that's going to deal with scale factors in 3D objects. The learning target is to be able to solve problems that involve a scale factor, surface area, and volume. Now, I'm just going to let you know that I'm doing this video series in the last block of a Thursday, and so if a bell goes off or an announcement goes off, I'm just going to continue through it, and I apologize for any interruptions. So you might recall from a previous section that we looked at what happens as far as areas when we start to scale things up. And you should remember that the net result was basically a factor of k squared. So if I took a two-dimensional figure and I scaled it up by 3, my area was affected by a factor of 9, or k squared. So what we're now looking at is what happens in 3 dimensions when we talk about surface area and volume. So you can see here that I just have the formulas that you would have learned in grade 10 for surface area and volume of a couple of different shapes, or different 3D solids, I should say. And so what we're going to do is we're going to jump right into an example, and we're going to try and examine deductively, so using kind of a deductive proof to jump all the way back to what we did in September, we're going to deductively try and show what the relationship is between the surface area and the volume when a rectangular prism gets scaled up. So if you think about it, if I have a rectangular prism starting off with, so let's call this my rectangular prism, and let's say I take this, and let's say it had a length, and I'm going to call this length, this width, and this height. Well, you think about what happens when we scale something up. It's the idea that I'm going to take each of these things and I'm going to multiply by my scale factor of k. So all of a sudden I don't have w as my width anymore. I've got k times w, and I've got my height times k, and I've got my length times k. So if we go back to thinking about, probably volume is the easiest one to start with. If we go back to thinking about the volume of this new shape, so I'm going to put volume new, recognizing that the volume of the old shape, so I'll go volume old, the volume of the old shape would have been w times h times L, or any order would have done. So the volume of my new one is now going to be, well, instead of W, I have K times W. And instead of my H, I've got K times H. And instead of my length, I've got K times my length. And so what you'll notice is if we look at this, okay, I've got K times K times K. Again, multiplication is associative, and it doesn't matter what order. It's also commutative, so I can switch around the order here. And if I factor out all my K's, I end up getting K times another K, and in the end I end up having this W, H, and L. Well, we can simplify this. K times K times K is going to give us K cubed. And W times H times L, well, if you think about it, that is actually the volume of the old rectangle. So I'm going to substitute volume old in here. So the volume of the new rectangle is simply k cubed times the volume of the old. So net result here, what's happening when we scale up by a factor of k? Well, algebraically, we've shown that we're actually going to scale up our volume by a factor of k cubed. So scale factor, or if we scale up dimensions by k, we scale up volume by k cubed. Alright, now the next thing we want to look at is we want to look at the surface area. So if we just go back right quick, you can see surface area is going to be 2 times length width, length height, and width height all combined. So that's typically our older one. So if we just want to write that out, let's grab a different color. So we're going to say new proof. So surface area of what I'm going to call old is 2 times, and again it was LW plus LH plus WH. And again, so what we want to look at is what would the surface area of a scaled up figure look like? Well, we still have 2, but instead of L, we now have KL. And instead of W, we now have KW. And likewise for these other terms. So I'll just quickly put in KL, KH, KW, and KH. So hopefully, similar to what we did up here, you're noticing that we have a K times K, and a K times K, and a K times K. So if I just clean that up a little bit, you'll notice that I actually have K squared LW plus K squared LH plus k squared WH. And so there is a common factor of k squared here, so I'm going to factor that out in front, and I'm going to take it out all the way to the very front, because I kind of want to show you something that what we're left with if I factor out that k squared is 2 times, what would be left in here? Well, we'd have LW plus LH plus WH. And so in this case, if you notice what happens, this in blue is really the surface area of our old rectangular prism. So what's happened is that we've actually gone up by a factor of k squared, which was kind of consistent with what we saw when we did the two-dimensional figures. We saw that it went up by a squared factor here. Well, again, it's going up by a squared factor. Now, a really good question I would have is this always going to work? Like, for example, if we looked at a right triangular prism, will this still work? So let's take a quick look at what happens with the volume of a right triangular prism, and let's look at what happens with the surface area of it. So let's start off with volume. So the volume is 1/2 the base times the height times the length. So again, we're doing our triangular prism now. And we have our base, we have our height, and we have our length. So the volume, and I'm going to jump immediately into scaling this up, the volume would be 1/2. Instead of base, I'm going to get KB times my height, so I'm going to get KH, times my length, so I'm going to get KL. All right, and so now what's end up happening? We get 1/2, and you can see we have KKK, so we've got K cubed, and then we end up with the BHL here. If I wanted to factor that out a little differently, I could say that's K cubed times 1/2 times BHL, recognizing that this is the volume of the old unscaled solid. So really I've got, again, a factor of K cubed coming out versus the volume of my old solid. Now the surface area formula is a little more involved here. So we've got surface area is base times height plus the length times A plus B plus C. And we can see A, B, and C are the sides of that triangle. So surface area is base times height plus L times A plus B plus C. So if we look at surface area of the new, well, initially we had base times height, so we're going to get KB times KH plus, and then we would have had L, so that length is going to be KL now. And even A, B, and C, they all would have been scaled up by a factor of K as well. So I get K times A plus K times B plus K times C. So I can see that in this, I have a factor of K squared, so I've got K squared BH. In this, inside here, I've got a factor of K, so I'm going to factor that out in front, and maybe I'll show all my steps here. So I'd end up with K times A plus B plus C. And then these two K's will actually create a K squared for me. So I've got K squared times BH here, plus, and I get K squared times L times A plus B plus C here. And so if you notice, well, I can factor out a K squared again, and I'm going to get left with these two red pieces. So I'd end up with K squared multiplied by BH plus L times A plus B plus C. And hopefully you're recognizing that, hey, that's actually the formula for the surface area of the unscaled triangular prism. So again, we're getting that factor of K squared coming out in our area, and this is basically the surface area of the old figure. So it seems like every time we scale up a figure by K, its volume goes up by a factor of K cubed, and its surface area goes up by a factor of K squared.